Hello, and thank you for joining me today. I'm delighted to have the opportunity to discuss my research interests and ongoing studies that sit at the crossroads of innovation in photonics and materials science. My journey in this field is fueled by a deep curiosity and a commitment to advancing our understanding of light and its interactions with various materials. Silicon photonics is the cornerstone of my research. This fascinating area allows us to use silicon, traditionally a workhorse of the electronics industry, as an optical medium. The precise patterning of silicon into microphotonic components has profound implications for telecommunications and beyond, particularly at the 1.55 micrometer wavelength. Alongside this, I'm exploring the realm of photonic crystal fibers and waveguides. These structures harness the power of light in innovative ways, guiding it with precision for applications in telecommunications, sensing, and more. The phenomenon of supercontinuum generation also captures my interest. This process allows us to generate a broad spectrum of light, which has potential applications in spectroscopy, metrology, and as a tool for exploring new aspects of light-matter interaction. In the material sciences, I'm particularly drawn to chalcogenide glass materials and devices. Their unique optical properties make them suitable for infrared sensing and integrated photonics, presenting a rich tapestry of research opportunities. The pursuit of clean energy solutions guides me towards photovoltaics and thin-film solar cells. I investigate the forefront of materials science to improve the efficiency and affordability of solar energy. In the field of plasmonics, I am fascinated by the manipulation of light on the nanoscale, which promises to revolutionize sensing, imaging, and perhaps even computing. My interest in biophotonics allows me to contribute to the cross-disciplinary bridge between photonics and the life sciences, where light-based technologies can be used for medical diagnostics and research. The exploration of micro and nanostructures involves delving into the minuscule, creating materials with novel properties and applications that are not possible on larger scales. Metamaterials and graphene absorbers represent the cutting edge of materials that can be engineered to have properties unlike anything found in nature, providing new mechanisms for controlling light and electromagnetic waves. Lastly, the intersection of photonics with artificial intelligence in AI-based photonics represents a leap toward the future, where smart systems can optimize themselves for a variety of applications, making our technologies more efficient and capable. Each of these interests is a piece of a larger puzzle in understanding and utilizing light in novel ways. As I continue my research, I am inspired by the potential for discovery and the profound impact these studies can have on technology and society. My research interests are centered on the innovative field of silicon photonics. This area represents the nexus of optical and electronic technologies, where I delve into several key aspects. I am intrigued by the study of ring resonators and their applications in photonic circuits, due to their ability to selectively resonate certain wavelengths of light, making them valuable for optical filtering and multiplexing. I explore various coupling mechanisms for efficient light routing in photonic chips, which includes broadband and directional couplers, BDC, and grating couplers, GC. My interest extends to interferometers, such as Mach-Zehnder and Michelson, which are fundamental in modulating and sensing light for a wide range of applications, from communications to sensor technology. I examine the design and function of splitters and combiners that manage the distribution and combination of optical signals, essential for routing light in complex photonic circuits. My research investigates the role of tapers and terminators in reducing reflection and scattering losses, ensuring that light is effectively guided through photonic components without unwanted disruption. I am fascinated by Bragg gratings and their capacity for filtering light within a photonic waveguide, which serves various applications from telecommunications to sensing. The study of photonic crystals captivates me due to their ability to control the flow of light in 2 or 3 dimensions, which opens possibilities for manipulating light at the sub-wavelength scale. Logic gates. Investigating optical logic gates is part of my interest, as they are the building blocks for optical computing and could revolutionize data processing speeds and energy efficiency. Low pass, band pass, high pass, notch, and add-drop filters. My research also encompasses various optical filters, each with a distinct purpose in controlling spectral components of light, which is crucial in communication systems and signal processing. I am keen on the development of optical coders and decoders for high-speed data transmission, which play a vital role in optical networks and data centers. I delve into the principles and designs of multiplexers and demultiplexers, which enable multiple optical signals to be combined into a single channel and separated back into individual signals at the receiver end, optimizing bandwidth utilization. Converters, analog to digital and digital to analog converters. My interest in converters involves transforming analog signals to digital and vice versa in the optical domain, which is a key function in integrating photonics with electronic systems. This array of topics showcases my passion for pushing the boundaries in the realm of silicon photonics, aiming to harness the power of light to drive the next generation of technological advancements. My research focuses on both linear and nonlinear aspects of photonic crystal fibers, PCFs. I examine the effective index and dispersion, crucial for controlling light within PCFs, and losses from waveguide imperfections and physical manipulations. Additionally, I study the effective area and numerical aperture to enhance light handling in PCFs. For the nonlinear parameters, I analyze the gamma value's influence on light's behavior within PCFs. Utilizing the nonlinear Schrödinger equation, I model light propagation under diverse scenarios. The split-step Fourier method is key in my simulations, providing precise insights into light's journey through PCFs. This comprehensive research aims to drive innovation in photonics, with broad applications from telecom to healthcare. My research is centered on photonic crystal waveguides, the cornerstone for precision light control in advanced photonic devices. I investigate ring resonators and optical switches for wavelength management, and delve into multiplexers and demultiplexers, which are critical for efficient data transmission. My work also encompasses T and Y branches that steer optical signals, and power splitters, along with various filters that shape light for communication technologies. Further, I am pioneering logic circuits using these waveguides to pave the way for all optical computing. By integrating these components into sophisticated systems, including coders, decoders, and memory-centric flip-flops, my goal is to harness photonic crystals' potential to transform information processing. In my research, I utilize the finite difference time domain (FDTD) approach to delve into solar cell properties, optimizing light absorption, reflection, and transmission to boost efficiency. A prime focus is on elevating the photon-to-electron conversion rate, crucial for the cell's effectiveness. I also assess solar cells' electrical aspects, including the correlation between the short-circuit current and open-circuit voltage, alongside power voltage characteristics. The filling factor, indicative of cell quality and power potential, is a key interest. My goal is to merge FDTD analysis with electrical simulations, aiming to develop more efficient solar technologies. COMSOL Multiphysics is our go-to tool for numerical simulations due to its broad modeling capabilities across various scientific fields, user-friendly interface, and accurate results. It shines in handling complex multiphysics problems, allowing us to simulate real-world phenomena with precision. We've used COMSOL Multiphysics to see how light travels through optical fibers, including both the standard types and those with special crystal structures. This simulation helps us aim for quicker and more reliable internet connections by manipulating light paths. Our work with COMSOL includes designing components like waveguides, filters, and multiplexers within photonic crystals. These simulations are crucial for creating devices that control light in innovative ways, paving the path for advanced optical technology. We also utilize COMSOL to simulate the behavior of mirrors and lenses, predicting how they focus and direct light. This is key for developing more effective optical instruments before they're physically made. In biophotonics, COMSOL simulations help us understand the impact of light on biological tissues, particularly in the brain. This includes exploring how light propagates, transfers heat, and its distribution within biological media. COMSOL is instrumental in simulating how electromagnetic waves traverse the human head and brain. These simulations are vital for assessing the safety of electronic devices and enhancing medical diagnostic methods. For laser technology, sensors, and optical circuits, we model resonators and optical splitters in COMSOL. This helps us refine these devices to control light with high precision. We employ COMSOL to simulate electro-optic modulators, aiming to improve the efficiency of communication systems. These simulations guide us in using light for faster information transmission. COMSOL is used to design plasmonic filters, tiny devices that could revolutionize sensing and photonic circuits by manipulating light at the nanoscale. We leverage COMSOL to model and enhance solar cells, focusing on increasing their ability to convert sunlight to electricity, thereby contributing to sustainable energy solutions. Our simulations in COMSOL extend to graphene absorbers and metamaterials, investigating their interaction with electromagnetic waves to discover new applications in energy and sensing technologies. Photoacoustic imaging improved through COMSOL. By combining optical and acoustic simulations in COMSOL, we advance photoacoustic imaging techniques which have the potential to transform medical diagnostics. In COMSOL, we simulate piezoelectric materials to design innovative sensors, actuators, and devices capable of energy harvesting, moving towards smarter material applications. We use COMSOL to develop models for biosensors and detectors, aiming to revolutionize diagnostic tools for health monitoring and environmental safety. Our simulations in COMSOL improve the design of MRI coil windings, aiming for enhanced clarity in medical imaging and diagnostics. Lastly, COMSOL simulations are applied to study plasma, with implications for energy production, space exploration, and electronics manufacturing. Each of these simulations, made possible by COMSOL Multiphysics, demonstrates our commitment to using cutting-edge computational tools to spearhead advancements across a wide range of scientific and technological fields. Thank you very much for attending my presentation and for dedicating your valuable time to it. Your attendance was greatly valued. I eagerly anticipate any questions, recommendations, and insights you might have concerning the project. Your expertise and guidance are of immense importance to me, and I am keen to benefit from your feedback. Once again, thank you for your support and active participation.